Listo, profesora.
¿Ya está grabando? Bien,
Así es, profesora.
bueno. Bueno, buenos días, bienvenidos a la charla de hoy de la Red Latinoamericana de Física de la Materia Condensada y Ciencia de Materiales, la red LAFMAT, que es una red sin fines de lucro, una comunidad que tiene como objetivo poner en contacto a investigadores de distintos países latinoamericanos, entre ellos y con países del primer mundo. em, y cuyo objetivo es favorecer la colaboración entre los distintos investigadores y entre los distintos países. Esta red está integrada por miembros de universidades de distintos países de Latinoamérica, entre ellos incluidos Perú, Brasil, Colombia, México, Venezuela, Chile, Argentina, Bolivia, Costa Rica, Ecuador y El Salvador. Esta red provee una plataforma para que la investigación avance, para que compartamos nuestros conocimientos y se incremente la visibilidad de la ciencia latinoamericana. Today we have the pleasure uh, to welcome Professor Amangeldy Zhunusbekov from the Department of Technical Physics at Gumilyov, Eurasian National University in Astana, Kazakhstan. Professor Zhunusbekov is a researcher who is interested in solid-state physics, luminescent materials, radiation-induced phenomena, and the optical properties and advanced ceramics, and crystals. Today, he will share his research on luminescent properties of ceramic based on metal fluorides, highlighting the optical properties of these materials and their potential applications. So thank you for being with us, Professor Amangeldy. Now,
Thank you very much. I can start.
yes, now we can see your presentation.
My name is Amangeldy Zhunusbekov. I'm from Kazakhstan. Allow me at present my report. First, I would like to tell you about my country. A few slides about Kazakhstan and then about our research. Kazakhstan of the world map, Republic Kazakhstan has ninth largest country in the world by area. Kazakhstan has large reserves of minerals and energy resources. This is history of our country, Kazakhstan. The first region where horses were domesticated, descendants of the Huns, one of the reasons to the fall of the Western Roman Empire. And the next slide, our difficult periods in our history began after joining Russia. This is historical facts about difficult periods in our country. Very population were died in this period. 1931, 1933 years. Now we Kazakhstan is silk way from China to Europe, and yeah. This are our culture, language, and heritage. Okay, next stage our report is our scientific research work. Now we move on to our research work. One of our department's research areas is the synthesis and study of functional materials. One of the current direction in modern material science is the development of ceramics materials based on metal oxides, fluorides activated by multivalent ions. Such materials exhibit high transparency, radiation resistance, and the possibility of controlled modification of luminescence properties. Luminescence materials are extensively used both in lighting technologies and scintillation detectors for medicine, industry, and high energy physics. In our work, we synthesize ceramics materials based on metal fluorides. Conventional high-temperature synthesis of fluoride ceramics is accompanied by losses of activators due to the formation of volatile compounds and the deterioration of materials properties. Radiation synthesis makes it possible to overcome this limitation by enabling activators incorporation without additional additives and by producing homogeneous radiation-resistant ceramics. We are interested in NGF2, BAF2, and BAMGF4 ceramics activated with tungsten. These ceramics combines the properties of BAF2 and MGF2, possess a stable orthorhombical structure and allows the formation of Efficient luminescence center. We are investigating the luminescence properties of MgF2, body F2, and BMGF4 ceramics materials activated with tungsten and obtained by radiation synthesis without the introduction of additional substance that facility activities incorporate. This slide presents the experimental setups used in the research. They played a key role in conducting the experiments and ensured the reliability and accuracy of the obtained data. For the synthesis of ceramics from refractory inorganic materials, and experimental setup based on the LV6 electron accelerator of the Institute of Nuclear Physics on Novosibirsk was used. The scheme of which is shown in this slide. This accelerator is capable of generating an electron beam with energies ranging from 1.4 MeV power stage, and all characters shows in slide. Electron beams was deflected in one plane at a frequency of 50 GHz, while the target was moved perpendicular to the beam at a speed of 10 millimeters second. This configuration allowed for uniform irradiation of crackers measuring in practice, each point of the surface was exposed to short electron pulse with a duration of about millisecond. And due to scanning of uniform dose distribution over the entire sample area was achieved. After radiation, we have ceramic samples based on metal fluorides activated with tungsten. We obtain figure 3, view of synthesis samples of MgF2 and with various ions from tungsten ions. Figure 4 shows same analysis spectrum of the element composition of the study. We see elements Mg of F, tungsten is body. Next slide, results of mapping the distribution of elemental composition of samples. This slide shows same image of BA-MGF4 and the BA-MGF4 with tungsten oxide. Structural investigation of BA-MGF4 ceramics using X-ray diffraction. X-ray diffraction confirmed the formation of the main BA-MGF4 phase. The X-ray diffraction methods made it possible to determine the crystal lattice parameters. Is shown in table 1 of this. In table 414 angstrom. The material density was 4.5 grams cubic centimeter. The table presents the comparison of our result with those reported by all the researchers. The comparative data indicate a high degree of structural ordering in the obtained ceramics. The crystallite size was approximately 41 nanometers. Phase analysis confirms the exceptional phase purity and the homogeneity of the synthesis samples. These results confirm the successful synthesis of tungsten activated BA-MgF for ceramics obtained via radiation synthesis without the addition of foreign substance that activated incorporation into the crystal lattice. This slide shows excitation spectra of the investigation samples for non-activated MgF2, BAF2, and BAMGF4 matrix. Single maximum accept approximately 220 nanometer is observed corresponding of two intrinsic matrix transition. In the activated MgF2 with tungsten, this figure is 11. Figure 12 shows the photoluminescence spectra of BAF2 with tungsten. This slide shows luminescence and luminescence spectra and the excitation 220 to 145 nanometers. This mechanism this slide presents the energy diagram of excitation and relaxation process in BAMGF4 and BAMGF4 with tungsten ceramics. In non-activated crystal ceramics, luminescence in the 44 450 nanometers. Region is attributed to transition involving defect centers in the matrix formed during radiation synthesis. These defects create localized states within the band gap through which radiative recombination of charge carriers occurs. Activation with ions tungsten, the energy structure of the materials changes, new impulse levels are formed. As such, use tungsten-related centers and fluoride vacancies, F centers. This leads to the appearance of an intense luminescence band in the 500 nanometer regions. Thus, the introduction of tungsten oxides modifies the charge carrier relaxation mechanisms, creates more efficient radiative channels, and enhance the luminescence intensity of ceramics. This slide presents the integral cathodoluminescence spectra. Cathodoluminescence spectra figure 16 shows pulsed cathodoluminescent spectra of ceramic samples measured 10 nanoseconds. And the 17, we see kinetic curves of cathodoluminescence. You say with the without ions of tungsten, we saw in figure in B. This is next stage. We study of luminescence from defect centers in ceramics materials and the VUV synchrotron excitation at 9 Kelvin was performed. This experiment was synchrotron DAISY in Hamburg, Germany. This slide presents three-dimensional luminescence and excitation spectra in the 410 energy range. In this range, BAMG4 F4 ceramics and 9 Kelvin exhibit intense luminescence in the this 300 for 550 nanometers. The highest intensity is observed in the excitation energy range of 6 and 8 electron volt, where in the 300 and the B figure B shows in the high energy region the spectral behavior changes significant. The main contribution to emission comes from the band at 336 nanometers, while the intensity of the 372 nanometers band increase. This slide presents the excitation spectra of luminescence in BAMG4 MgF4 ceramics recorded for different emission wavelengths. We see this 4 regions. 336 to 470 nanometers. Analysis of the spectra shows that luminescence excitation occurs through several energy channels in the intermediate energy range. Pronounced excitation maxima observed particularly for emission at 336 and effects in excitation of excitons states and their involvement in energy transfer to luminescent center. In the high energy regions, intensity excitation peaks are observed most pronounced for the 336 nanometers emission. Next slide presents the luminescence spectra of our ceramics materials recorded under excitation energy of 6 electron volt. 6 and 9 electron volt. Under 6.6 electron volt excitation, the luminescence spectrum exhibit of complex structure and can be representing as a sum of several components. The spectrum shows bands with the maximum and emission energies of approximately some electron. What this is, we see 3.7, 3.3, 3.5, 3, 2.8 electron volts. This compression of the spectral and the excitation shows that change in the excitation energy lead of registries of the contribution of excitation and defect centers, which determine the luminescence mechanism of VAMGF for under both excitations. This slide presents the energy diagram of excitation and relaxation process in VAMGF for ceramics under vacuum ultraviolet excitation. Under VUV excitation, electrons are permitted from the valence band to the conduction band, after which the energy relaxes through several competing channels. The first pathway is associated with the formation of self-tracked excitation, self-tracked excitons. The radiative relaxation leads to photon emission with an energy approximately. The second relaxation channel occurs via defect centers in the crystal lattice, which form localized states within the band gap. Transition through these states result in longer wavelengths emission in the 3.55 and 2.88 electron volt range, corresponding to bands associated with defect in this luminescence. This scheme shown clearly demonstrates that luminescence in our ceramics and the VUV excitation is formed as a result of the interplay between interband transition, excitation, relaxation, and defect-related channels, which is fully consistent with the experimental excitation and emission spectra. All thank you for attention.
Thank you very much, Professor Amangeldy. Thank you very much for your presentation. Very, very interesting research. Now we proceed to go for the question session. We could go through the panelists of the of LAFMAT, of the network. Would you like Professor Carlos Rudamas to ask a question?
Yes, can you hear me?
Yes.
Thank you very much, Professor Amangeldy, for the interesting talk about the luminescence properties of your ceramics. My question is the following. I think you made an interpretation of your transitions. Have you tested if this interpretation is fine? For instance, making experiment like power density dependent luminescence.
Yes, so we make experiments.
Did you make a power density dependent luminescence experiments?
Could you repeat that?
Power density, electron
Exactly.
beam.
If you change my question is, if you, for instance, if you change the power of your excitation on when you make this kind of PL for photoluminescence or luminescence experiment, depending on the power, the excitation power.
Excitation power.
Quizás pueda escribirle en el chat, Carlos.
Okay. Okay.
Can you write in chat?
Power dependent luminescent experiment.
Exactly. The idea is that when you change the power, the behavior of the luminescence is different for different transitions. For instance, defect related transition or free exciton related transition. The behavior is different. For instance, the slope is different.
With experiment, we did not yet.
Okay, because this could be a very nice and relatively easy way to test the origin of the nature of the transitions.
Yes, thank you. We will be this experiment make.
Okay, we will be in touch in order to talk about it. Yeah, thank you very much, Professor
Yes.
Manan.
Okay. Is there any other questions? Is there any other panelists who would like to ask a question? In the meantime, I could ask something. What are the applications of these materials in particular? What's the application of this of studying these ceramics, this luminescence? Professor Amangeldy, your micro is off.
Sorry, I did not understand.
I was writing to you in the chat. What are the applications of this topic?
And I understand. This application is scintillation detectors for medical imaging, phosphors for UV and LED light sources, vacuum ultraviolet and ultraviolet photonics devices, radiation dosimeters, sensor system.
Okay, thank you. And the defects, do you control where you generate the defect? If, let's say, if it's interstitial or when the first part of the talk, when you were talking about defects, doping the samples.
Defects formation in process synthesis electron beam in ceramics. During electron beam process.
But my curiosity is about where are the defects? Are in the interstitial or or they substitute another atom?
The defects are located inside the crystal lattice with the energy levels within the band gap.
Okay, we will follow your research because it's very interesting. Are there any questions in en las redes, Jimena?
Profesora Gabriela, buenos días. Expositor, también buenos días. No tenemos preguntas en nuestras redes. Solo mencionan lo interesante de la charla y el diferente tópico que tenemos el día de hoy. Muchísimas gracias.
Gracias. Well, there are no more questions in the net, so we will all switch on our cameras. Well, in case you want to say something, Professor Amangeldy, and we can switch on our cameras. So say.
Thank you for attention.
Well, thank you very much for being with us. And in case there are no more questions, we can all say goodbye to the next talk, and we can contact Professor Amangeldy using the email or somehow. We can
Thank
contact
you.
him.
I'm sorry, I can't switch my video camera.
Okay, no problem. Okay, goodbye.
Thank you very much, Professor Amangeldy. Nice presentation.
Thank you.
Thank you.
Thank you. Hasta luego a todos.
Luego. Adiós.
Luego, gusto verlos.